1951, Richard Feynman published a paper entitled The Concept of Probability in Quantum Mechanics, where he claimed that classical probability theory was not applicable in quantum mechanics, but that rather one would have to have separate laws of probabilities of quantum mechanics. I quote his main argument. We might at first suppose, since the electrons behave as particles, Feynman says, that 1. Each electron which passes from a source S to some location X must go either through hole 1 or hole 2. As a consequence of 1, we expect that 2, the chance of arrival at X should be the sum of two parts, P1, the chance of arrival coming through hole 1, plus P2, the chance of arrival coming through hole 2. However, we know from experiment that P is not equal to P1 plus P2. Hence, experiment tells us, so Feynman definitely that P is unequal to P1 plus P2, or that statement 2 is false. We must conclude that when both holes are open, it is not true that the particle goes through one hole or the other.
This microphone.
Oh, I didn't recognize that it was gone. And this conclusion was soon shown to be not true. Actually, just a few years later, there's a paper by Koopman, and then later very nicely summarized by Valentine, showing that the argument of Feynman draws its radical conclusion from an incorrect application of probability theory. What you have to use is conditional probabilities. You have to take care of the contexts. The context of the left slit open, the context of the right slit open, and the context of two slits open are three different contexts. And you cannot just compare, so to say, apples with pears. And of course, the experiment shows that these probabilities are different because you compare different contexts. And Valentine goes through classical probability in a very nice didactic paper showing that the superposition principle for amplitudes is in no way incompatible with the formalism of classical probability theory. So starting from this introduction, my argument will now be that if we start in the wave picture, instead of simply assuming that quantum systems are just particles, and of course the wave picture is also motivated by this beautiful analogy by Yves Coudet, which we just saw, that one could have a bouncer, an oscillator in some medium, interlocked and oscillating in phase with each other. And we shall actually, throughout the last years, we developed a model reproducing quite some general features of quantum systems with this classical type of model. And so we start with the wave picture, and we can show that the probability, the two probabilities actually sum up as in a classical case. So what we do is we calculate the wave intensity distributions, which then are correlated with the particle distributions. Consider, for example, the classical double slit. You have the intensity immediately after the slit. It is composed of the intensity from the first slit and the interference with the second slit. So you have just one slit on the side and the interference with the other slit. And the total intensity, of course, is average intensity, of course, is as we know it. Now, there's an analogy in quantum-like modeling, as we do, or in quantum mechanics generally, which I have written down here also for the general case for n slits. However, there's one additional important ingredient. And this ingredient has to do with the dispersion of a wave packet. Consider, for example, Coudet's analogy of the bouncing particle bouncing in a wave-like environment. Then, of course, in the long run, the particle will not only propagate in the forward direction, but will have diffusions to the right and to the left on the average. So we have a broadening of whatever distribution we start with, and this broadening is described by a diffusion velocity. in our model, which is closely related to Edwards-Nelson's diffusion or osmotic velocity, so that the total velocity field is composed of the forward velocity plus the deviating diffusion velocities either to the right or to the left. And the particular structure of this diffusion velocity is that it doesn't necessarily fall off with the distance, which has very important consequences. And this touches the issue of non-locality and even superluminal effects, and that's going to be a subject which I don't have time for here right now, but Jan Walecek will discuss this in detail tomorrow. What I want to show here is that, in effect, we have 3 current channels per slit, V, UL, and UR. And if we do that, we can model the decay of a Gaussian wave packet, and it turns out that this can be described completely analogously in a classical physics sense via so-called anomalous diffusion, where you can substitute or insert or define a time-dependent diffusivity, d of t, as it's written here, such that the expression looks like a Brownian-type displacement with the set time-dependent diffusivity. And from that, you can then derive directly the average total velocity field of a Gaussian wave packet, which is given by this expression. We have simulated this with very simple computational tools, coupled map lattices. So you have just a simulation program for diffusion, the only difference being that the diffusivity is now time-dependent. And the meaning of the time-dependent diffusivity is that this reflects a changing thermal environment. So once the particle is within the confines of the slit, the thermal environment is different to when it exits into the free, so to speak. So you have 2 situations here with a broad slit and a narrower slit. And in the narrow case, you see that the thermal environment somehow produces more momenta pushing the particles to the side, either to the left or to the right. Anomalous diffusion is a signature of superstatistics. The prototype of superstatistics is a Brownian particle moving through thermally changing environment. So, for example, for the particle, you have a relatively fast dynamics, the velocity on a small scale, and the slow changes due to the temperature fluctuations on a large scale. So you have the superposition of 2 statistics, and that's what's called superstatistics in the literature. The interesting thing is that this has unexpected emergent properties on intermediate scales. And we'll have another talk today by Petr Žisba, who is going to go in much more detail on this with respect to emergent relativity. So the interesting thing is that superstatistics has 2, if you want, extreme scales which produce emergent properties on the immediate scales. Now, this might be a nice analogy for modeling of quantum systems. Quantum behavior might emerge from the interplay of classical processes at the small subquantum and large macroscopic scales. That's why we introduced the term superclassical physics in analogy to the superstatistics just mentioned. So the interesting part again would be that emergence would happen through the co-evolution of those microscopic local processes and of the macroscopic boundary conditions. And even more interesting would be that then new types of behavior might be possible due to emergent features which are unexpected from either the small or the large scale. So that might be some curious phenomena, and actually in the discussion on trajectory-based models of quantum theory like Bohmian theory, people raised doubts because of such just very unexpected or strange phenomena. There's a famous paper by Marlon Scully on surreal trajectories. He said, do Bohm trajectories always provide a trustworthy physical picture of particle motion? Because he did not expect what Bohmian mechanics proposes, namely the non-crossing of trajectories. Here you have an interferometer where the last slab is removed, and Bohmian theory to the left shows this strange kind of repulsion whereas Scully argues quantum mechanics would show the opposite phenomenon. Now we know, at least from Professor Steinberg's experiments, that for the interference of photons at a double slit, one sees trajectories which do behave like the ones predicted by Bohmian mechanics. Let's go back to the total velocity field I just mentioned that we calculated from classical approach. Then we obtain an action function, which is essentially the classical action function plus the intermediate term, a kinetic energy term representing the temperature environment of our bouncing particle. Now, of course, the trajectories are the gradients over this action, orthogonal to surfaces of constant action, but they are not identical in general with the rays of geometrical optics, except in very simple cases like when there's a wave coming from a single point source. However, what happens in the case of 2 point sources, for example? Now here we have a comparison of the quantum case streamlines versus the geometrical rays. And Michael Berry compared them very nicely, saying the streamlines of the superposition are different from the superposition of the streamlines. And what you can see in the quantum case, the velocity field is somehow surreal, but actually it's an emergent velocity field. It's just by the interplay of all those components which somehow make the appearance as if they would slightly repel each other. Then, of course, to continue this story, there's this important paper by Howard Wiseman showing that the real parts of the weak values of the velocities are the Bohmian velocities. I mentioned already the Steinberg group's paper on weak measurements of photon trajectories. We can now ask new questions with regard to these trajectories, and we can even ask questions going beyond what we know from the Bohmian approach. We might, for example, ask, where does the guiding equation or quantum potential actually come from? Because one of the accusations was that it somehow comes from an invisible hand. There's just a very unintuitive element in this Bohmian picture. But our proposal is it could come from the concept of emergence. Consider, for example, just to give an example of emergence, a Rayleigh-Benaz cell. It's an open system. You have a fluid heated from below. There's a temperature gradient. You have trajectories which represent convection rolls. And the interesting thing is that depending on the form of the boundary conditions, you get different particle trajectories, different behavior, as you can see in the comparison of these two situations. So what we have here is we have local microscopic interactions producing emergent macroscopic structure, which again influences those microscopic interactions. So there's a co-evolution of both the microscopic and the macroscopic parts of the system. And this we denote as relational causality. We have both the bottom-up and the top-down developments. Our claims are the following. The usual formulation of the de Broglie-Bohm guidance equation is of the invisible hand type. That is, somehow mysteriously reaching out from configuration space into real space. However, the guidance equation is completely understandable in a natural way, as Philip Pearl would say, in real coordinate space under the viewpoint of emergence. A basic characteristic of emergent systems can be described via relational causality. To illustrate that, we made a small computer program where we had a droplet starting, a classical fluid, a droplet starting in the middle of those four squares and then moving in one of the directions, producing some kind of probability distributions in the long run. And then there's a different outcome. You can compare them, the different situations, although in the view that's shown here, nothing has changed. But if you take a wider view, then you see we embed the whole situation into above, which is limited by two mirrors to the right and to the left. It's producing standing waves, and these standing waves then act back on the local processes. If you now change the boundary conditions, like here, then you see that you have a change of the local probability distribution. So I just compare these two. This is what we illustrate. This is just for illustrative purposes. How we illustrate relational causality. Now, this then means that we have a co-evolution of processes stemming from the local slits and those from the global environment, including the boundary conditions. Now, we recall the classical double slit formula, as we have already seen, and now we look for the superclassical interference model. We now have, as opposed to what we had before, 3 channels per slit, as I said, due to the additional subquantum diffusion velocities, UL and UR, and they all 3 co-evolve. And I don't have time to discuss this diagram in detail, but what you see with the vectors kappa, they represent the emergent velocities out of the interplay of all those confluent channels. And I'll show you in more detail the outcome of the calculation, because it's, I think, a very simple and also elegant result. So we have, for n channels, we have 3 n velocity channels, which we denote with W, and we introduce the conditional probability for each of those velocity channels. All amplitude contributions of the total system's wave field are projected on that one amplitude at point x and t of one channel. And this is the expression, which is just a generalization of the formula we already have seen, except that now we have 3 velocity channels per slit in the system. And then, of course, you can define a local current, which is the intensity-weighted velocity. And then you can, I just skipped through that now, you can calculate all the currents which are present in the situation. And then you just sum up the total current for the 2-slit system, which is being the sum of all those local currents. And what you get is this result. This is the total current for the 2-slit system, with the last part being the genuinely quantum mechanical term. And in analogy, you can do that for n slits also very easily. Similarly, the total probability is the sum of the individual probabilities, and you can write that down. And finally, you get via the relation of the total current and the total velocity distribution, you do get the total velocity distribution, which is exactly the Bohmian velocity field, because remember that the U is essentially nabla R over R. If you insert in that, you get the result which you find in the Bohmian-oriented textbooks. So now, how do we get from there to the more familiar quantum notation? We use for the derivation of this an average orthogonality condition, which just means that the fluctuations to the right and to the left are unbiased. There can't be a bias in the direction where the diffusion goes. And then essentially it's the Madelung transformation, which we already saw today, which somehow constitutes the vocabulary from our language translating into the quantum languages. And if you do that, if you insert this language, so to speak, into our formula, you immediately derive the quantum mechanical probability density current, where the total psi is the sum of the individual psi's. And the same thing you can do for n-particle systems. I just state that here now. So what looks like the necessity to superpose wave functions in configuration space, the invisible hand type, can equally be obtained by superpositions of all relational amplitude configurations, that is, of waves in real space. And with these composition principles, as I just mentioned them, you derive the total velocity field for this n-slit system, which is just an average velocity field. For us, this was a really very nice and elegant result. And we could show, as I just indicated to you, that this is exactly identical to the Bohmian velocity field. So the guidance equation postulated by the de Broglie-Bohm theory is here derived and explained via the relational causality I just mentioned. Here, I've written all the three formulations in one slide. Our new derivation, which is just this averaged velocity field, the Bohmian one, and the usual quantum mechanical one. In the same vein, we obtain for n-slit systems Sorkin's first and higher order sum rules. There's no time that I go into detail about that, but they come out very nicely. And so in the effect, we have a correspondence with standard quantum phenomenology, in particular with Born's rule. The question would be, are there possible violations thinkable in our approach? Well, one thing is that at very small time scale, the model should break down, but there's a long time to go experimentally until one can check that. Another option would be to relax the mentioned average orthogonality condition. There might be some bias between UL and UR, which would then also violate, for example, Born's rule. As I mentioned, the discussion on superluminal effects and non-signal in principle will be touched upon tomorrow by the talk by Jan Walecek. I just finish skipping through our classical simulations of quantum phenomena like double-slit interference with weak dispersion, phase shifts, Talbot carpet. We reproduce the Talbot phenomenology very nicely, also quantitatively. Here, for example, we have a three-slit system where we vary the slit widths and play around with them. So this is all with our purely classical, very simple computer modeling. I skip the quantum Cheshire cat, let it disappear, oops. And this is our group. Without my colleagues, nothing of this would have been possible. Siegfried Fussi, Johannes Mesa-Pacasio, and Herbert Schwabel. Thanks very much.